Hello everyone. So today we are going to talk about one of the very important theorem in statistics, which is nothing but the central limit theorem. Very important as in academically as well as you can say for interview wise as well. It is very important because in an interview, if at all there are some chances that will be getting asked a question on statistic, then that question will be somehow definitely be related with the central limit theorem. Okay, so what is the beauty of this theorem and why it is so important? Well, let me just give you the brief idea about this and then we will see two examples which will make sure the theorem is clear to you. Okay, so what does the theorem say? Suppose you have a random variable x and it has some distribution. Okay, you don't know what is the distribution for x. Okay, so x is some population and whose distribution you don't know, and it has a mean mu and the finite variance sigma. Then the theorem says your x bar. What is x bar? If you recall my last lecture, x bar is nothing but the sample mean. It's a statistic. Okay, so it is a collection of the means of all the possible samples of size n. Okay, so this is a statistic, and if you find the probability distribution of x bar, which we call sampling distribution, then the sampling distribution for x bar will always be normally distributed. Okay, so when you try to plot the sampling distribution for x bar, you will always get a normally distributed curve, that is a bell-shaped curve with mean mu and variance. How much? Variance will be sigma square by n. So that's the beauty. Even without knowing the distribution of x, you can tell what is the distribution for x bar. And once you know that x bar is normally distributed, one can always use this transformation x bar minus mean of x bar, which is nothing but mu, upon standard deviation of x bar, sigma by root n. Right? We have seen this in my earlier lectures that one can always convert a normal random variable into a standard normal random variable with the help of this transformation x minus mu upon sigma. So here my x is x bar minus its mean and its standard deviation. And using this transformation we have the z values, and then we can solve the problems related to sample mean with the help of the z values. Okay, so we'll come to this later on when we will go to the problem part, but conceptually or theoretically let us first try to concentrate on this part. Let us try to understand this result with the help of an example. Okay, so to see the example, what I will do is I will consider a very small set so that the calculation will be easier and it will be easy to understand. Okay, so suppose your random variable x is taking the value 2468. Okay, now you take a sample of size 2. Okay, so let me call x1 here and x2 here. You take all possible samples of size 2. So how many will be there? So like I have 2, right? I have to choose 2 samples. So this has 4 possibilities. This has 4 possibilities. So total you will be having 16 samples. So you write down all the 16 samples of size 2. And then you find the mean, because I want to find the probability distribution of x bar. Okay, so we will write down the samples here and then we will find the mean for each of the sample, and then we will try to plot the probability distribution. So when I write down the possible samples, what are the possibilities? 22, 24, 26, 28, or 44, 42, 46, 48, 66, 62. So I am having these 16 samples. Okay, first sample, second sample, third sample. So I have written all the possible samples of size 2. After that you find the mean. So mean 2 plus 2 by 2, 2 plus 4 by 2, 2 plus 6 by 2. So this is the sample means, and this collection x bar is called as a statistic. Okay, so this is my sample mean. Now since this is a statistic, now I will draw the probability distribution of x bar, and what I should get is I should get that it is normally distributed. So what are the values? So you can see x bar is taking the value 2, 3, 4, 5, 6, 7, 8, right? So 2, 3, 4, 5, 6, 7 and 8. Correct? So this is what the values of x bar is taking. Now there are 16 values. How many times 2 is coming? I think only one time. So okay, so what is the probability of 2? 1 by 16. 3. How many times 3 is coming? 2 times. So probability of 3 is 2 by 16. 4 is coming 3 times. So it is 3 by 16. 5 is coming 1, 2, 3, 4. 4 by. So this will be 4 by 16. Then 6 is coming 3 times. 3 by 16. 7 is coming 2 times, 2 by 16, and 8 is coming 1 time, so 1 by 16. Can you see it's normally distributed? You see the curve. it is normally distributed. If you want to draw the histogram, this is how the histogram will look like. So you can see that your x bar is indeed normally distributed. Okay, you see your x is not normally distributed, your x is uniformly distributed. 2, 4, 6, 8. Each is having the probability of 1 by 4, 1 by 4, 1 by 4. Or if you want to draw the histogram, this is how the histogram will look like. So our x is uniformly distributed, but when we are finding x bar, you can see it is almost normally distributed, right? So that's what the center limit theorem says. Your x bar will always be normally distributed. There is some condition which I will come to it, but anyways, I hope this visualization is clear. Okay, so this is a sampling distribution for x bar. Okay, now that was one thing. Now if you try to find the mean of this, what is the mean of this? 20. So mean is 5. You try to find the mean of this expectation of x bar, it will come out to be 5, and if you will find the variance, it will be sigma square by n. Okay, so that I am not doing it, you can do that calculation. Okay, the theorem says expectation of x bar will be same as mu. In this case I can see 8 plus 2, 10, 20, 20 by 4 is 5. So if you will find the expectation of this, that means 2 into 1 by 16 plus 3 into 2 by 16 plus 4 into 3 by 16 and so on. If you will do that, your answer will come out to be 5. And if you find the variance of x bar, it will be nothing but variance of this. What will be the variance? Okay, whatever the variance comes out to be, I think variance will be 9 plus 1 plus 1 plus 9, 20. So variance is also 5. So variance will be sigma square. So 5 square by n. N is what? 4. So variance for this will come out to be 25 by 4. That I will not do, I will just keep it with you, I will leave it for you. But this is what the main observation is, probability distribution for x, but the nice probability distribution for x bar. Okay, so this was one example. Now let me take one more example where we will see that the more you increase the sample size, the sampling distribution will become more and more normal. Okay, now let's go for the second example. So here x is taking two values 0 and 1. So suppose x is a random variable which, like suppose if you are some quality manager in some manufacturing company, your job is to determine whether the product is defective or not. So you take a product, if it is defective, you assign 0 to it. If it is non-negative, if it's not defective, you assign 1 to it. Okay, so that's why for this experiment, what is my random variable? 0 for the defective item, 1 for the non-defective item. So this is my random variable. Now I will, suppose if I take the sample of size 1, okay, I'm taking sample of size 1. So I can either take only 0, 0. So 0 by 1, what is the average of 0? I'm taking only one sample, right? So 0 by 1 is 0. One sample size 1, okay, so I can choose 1. 1 upon 1 is nothing but 1. So 0, x will take the value, x bar will take the value 0 and 1, right? Because I'm taking the sample of size 1, that means I'm choosing only one element. So I'm choosing, if I choose 0, what is the average of 0? 0 upon 1 is 0. If I'm taking 1, what is the average of 1? 1 upon 1 is 1. So what is the probability of 0 and 1? 1 by 2, 1 by 2. Now suppose if I take n equal to 5, then what possible values our x bar can take? Okay, so now here 1, 2, 3, 4, 5. So either 0, 0, 0, 0, 0, that is one possibility. I am taking sample of size 5. Okay, another possibility 0, 1, 0, 0, 0, then 1, 0, 0, 0, 0, 0, 1, 1, 1, 0, and I can write down all the possibilities. How many such possibilities will be there? This has two choices, 0 and 1. This has two choices, 2, 2, 2. So 2 raised to 5. So there will be total samples. How many samples will be there? There will be total of 32 samples. Okay, so obviously I'm not going to write down all the 32 samples here. Space is also less, time is also less, but calculations are done. I have referred an online resource. So 32 sample size will be there, and what possible x bar it will take. So for example 0, 0, 0, 0, 0. So what is the average? Average is 0 only. X bar if I write 0. And how many there are? So 0 is coming how many times? 1 times. So what will be the probability of 0? 0. It will be 1 by 32. Then if you see here, what is the average of this? 0 plus 1 plus 0 plus 0 plus 0 by 5. So what is the average? 1 by 5, which is 0.2. Then you see how many times 0.2 will occur. Here you will see, you will get 3 by 5 means 0.6. If you take 2 times 1 will come, then it will be 0.4. If 4 times 1 will come, the average will be 0.8, and if 5 times 1 will come, it will be 1. So x bar will take the value 0, 0.2, 0.4, 0.6, 0.8 and 1. And now let me write down its probability distribution. Okay, so for n equal to 5, what did we get at the end? So x bar will take the value 0, 0.2, 0.4, 0.6, 0.8 and 1. And its probability is 1 by 32. So 0.03, 0.16, 0.31, 0.31, 0.16, 0.03. So this is what the probability you get. So I hope you got the idea how to find this from the earlier example. And here also I give you almost the hint how to get this. Okay. Then if I take sample of size 10, that means what? I am having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now each is having 2 possibilities. So 2, 2, 2, 2. So 2 raised to 10. So 1, 0, 2, 4 samples. How many samples will be there? All possible samples of size 10. There will be how much such samples? There will be 1024 samples. So if we write down all of them, the averages will come out to be, it will be either 0 or 0.1, 0.2, 0.3, 0.4, 0.9 up to 1. So this will all the possible averages for it. And if you try to find the probability, it will get 1 upon 1024. 0 will come only 1. So 1 upon 1024. Now since I am writing only till 2 decimal, that's why I have written 0.00. If you take some more decimals, then this will be non-zero term. But okay, I am just restricting it to 2 decimal. Okay, 1 will also come only once. So therefore 1 upon 1024. So this is also 0. And remaining, similarly we find the probabilities for other possibilities for x bar. When you take n equal to 20, so for 10 there were 11 terms. For 5 there were 6 terms. For 20 there will be 21 terms. 0, 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, 0.35, 0.30 and so on up till 1. And one can write down the probability distribution over here. Now that will be very big, that's why I am not writing. But what good thing happens here is now you observe the sampling distribution. One can observe a very nice thing. Now what is the sampling distribution for this? If I just let me draw this 0 and 1. 0 is taking one probability 1 by 2 and this is 1 by 2. So this is uniformly distributed. What about this? If you take this as 0, 0.2, 0.4, 0.6, 0.8 and 1. This is taking 0.03, 0.16, 0.31, 0.16, 0.03. You can see it's almost normal. Okay. Again, now if you try to draw this, let me erase this. When I try to draw this 0, 0.1, 0.2, 0.3, 0.4, 0.5. So these are all the possible values of x bar, and if you draw the probability distribution, this will take the 0, 0.01, 0.04, 0.12, 0.21, 0.25. Then again it will decrease symmetrically 0.21, 0.12, 0.04, 0.010. So again you can see it is normal distributed. So once you take larger and larger sample size, the probability distribution for x bar, which we call sampling distribution, will approach towards the normal curve. It will give you more and more nicer normal curve. Okay, so that's why one should always take a good large number of sample size. Question is how much large? Central limit theorem says you take sample size of at least 30, your x bar will always be normally distributed irrespective how bad your x is. However bad your x is distributed, your x bar will always be normally distributed. Okay, so it can be anything. So for example, even if the probability distribution for x is something like this or something like this or whatever, something like this. This is a probability distribution for x. If you take sample size of at least 30, and if you try to draw the probability distribution for x bar, it will always be normally distributed. So for even if this is x for x, this will be for x bar, x, x bar, x, x bar. So irrespective of the distribution for x, your x bar will always be normally distributed provided you take n to be at least 30. What is n? It is the size of the sample that you are taking. Okay, so this restriction you need if your x is not normally distributed. Okay, so if your x is not normally distributed, then the central limit theorem says you take sample of size at least 30, your x bar will always be normally distributed. But then if x is normally distributed, in that case what? Suppose your x is indeed normally distributed with mean, mu and variance sigma square. Then irrespective of the size of the sample, your x bar will always be normally distributed with mean, mu and variance sigma square by n. So that n greater or equal 30 is only required if your x is not normally distributed. If x is normally distributed, then you take sample of any size. If you take sample of size 1, it is same as x. It is normally distributed. When n is 1, you get the same thing. When n is 2, again if you try to plot the probability distribution for x bar will be normally distributed with mean, mu, variance sigma square by 2. If you take sample of size 3, again x bar will be normally distributed with mean, mu, variance sigma square by n. So when you have normally distributed random variable, x bar will always be randomly distributed. Okay, normally distributed. And when x is not normally distributed, then central limit theorem says x bar will still be this provided you take n greater or equal 30. Then you relax. And in real world, usually when you play with the data, you have the data set with 60 million, 70 million, 80 million lines. That's a huge data set. So when you take the sample, obviously you will take sample of size at least 30, because when you have huge data, you don't take sample of size 2 or 3. Okay, because you'll be playing with millions of lines. Okay, so that's why those who are in the corporate world, they don't know this thing. Like I still remember when I was in COEP, one of my college in Maharashtra, India. So there one fellow, he was talking about this central limit theorem, and he didn't even said even once that n has to be at least 30. It's not his mistake as well, because like when they play, as I said, when they play with the data, they have a huge data, so they always take sample of size at least 30. So for them it's like, yeah, if x is whatever the distribution x has, x bar is always normally distributed. Okay, but okay, now thanks for watching to my video, so you know that this condition is indeed there. Okay, so that's one thing. Now you may say, what about if n is less than 30? Well, then also this works provided your x is not terribly skewed. Matlab x is not that bad. Okay, suppose if your x is not normal, something suppose like this. It's not normal, but it's not that bad as well. Okay, it's almost kind of normal. So if your x is not terribly skewed or not too much distorted, okay, or is approximately normal, then in such scenario, even if you take n less than 30, then it will give you decent normal approximation, not the exact one, but the decent normal approximation. Okay, so that's what the main idea of central limit theorem is. Maybe in next lecture I will take some more examples, so this will be clear to you. But just to conclude, let me prove that if x is normally distributed, then x bar is always normally distributed. Why I want to prove this? Because it will make sure your earlier concepts are clear. Okay, that's the only reason I am proving this fact. Okay, and if x is not normally distributed, the central limit theorem proof is longer, so I am not going to prove that. But if your x is normally distributed, then x bar is also normally distributed with mean, mu and variance sigma square by n. Let us try to prove it. Now once you have a normal distribution x, you take a sample of size n, say x1, x2, x3 up to xn. And these are your IIDs. I talked about IIDs in earlier lecture. IIDs means what? These are independent samples and they are identically distributed. Okay, so if you take first sample, say x1, x2, x3 and xn. Then again you take a second sample of size n, third sample of size n, fourth sample of size n, and so on. They are independent. Identically distributed means what? If suppose this has probability distribution f of x, then x1 will also have the probability distribution f of x. This will also have the probability distribution f of x. This will also have the probability distribution f of x. So your random samples which you are taking, they are independent and they are identically distributed. Identically distributed means what? Your x and this x size all of them have the same probability distribution. Okay, then they are called, this xi's are called as IIDs, independently identically distributed. Well, actually, if you want, you can just pause and you can see the earlier part. When we took x to be 2, 4, 6, 8, the probability distribution was 1 by 4, 1 by 4, 1 by 4, 1 by 4. Then what was your x1? We took a sample of size 2. So x1, it was like 2, 2, 2, 2, then 4, 4, 4, 4, 6, 6, 6, 6, 8, 8, 8, 8. So 2 was repeating 4 times. So 4 by 16, which is nothing but 1 by 4. For 4, what was the probability? 4 by 16. For 6, 4 by 16. For 8, 4 by 16. So again, the probability distribution is same only, 1 by 4, 1 by 4, 1 by 4, which was same as that of x, 1 by 4, 1 by 4, 1 by 4, 1 by 4. Okay, so probability distribution of x will be same as the probability distribution of all these things. Okay, so since x is having the mean mu, it has a probability distribution f of x, so all of them will have the probability distribution f of x. Since they have the same probability distribution, so therefore mean of xi's will be mu and the variance of xi's will be sigma square, because the probability distribution is same, so therefore the mean and variance will also be same. Okay, so now we have this n independent IIDs. Then there is a nice result that if xi's are normally distributed, then its linear combination is also normally distributed. So if I take x bar, which is x1 plus x2 plus x3 plus xn by n, so this is nothing but 1 by n into x1 plus 1 by 2 into x2 plus 1 by n into x3 plus dot 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 1 by n into xn. So I am taking a linear combination of xn. Then by that theorem, this one theorem, linear combination of normal random variables, and if they are identical independent IIDs, which is true in this case, then this is also normally distributed, and therefore your x bar is normally distributed. Okay, n can be any size. Okay, so because of that reason, your x bar is normally distributed. Okay, and now what can you say about expectation of x bar? By property of expectation, it is 1 by n. Expectation of x1 plus expectation of x2 plus expectation of xn, which is nothing but n times mu, and n gets cancelled, you get mu. What can you say about variance of x bar? Means what can you say about the variance of x1 plus x2 plus xn by n? Well, if you remember in earlier lectures I told that what is variance of ax plus by? It is a square into variance of x plus b square into variance of y plus 2ab into covariance of xy. But when x and y are independent, covariance is 0, so this is what you get. And this gets generalized to higher dimension as well. So if x1 to xn are independent random variables, then variance of this is a square, right? So 1 by n square variance of x1 plus 1 by n square variance of x2 plus 1 by n square variance of xn. But all of them have the same variance, sigma square. So 1 by n square into sigma square plus 1 by n square into sigma square plus 1 by n square into sigma square. So n times sigma square upon n square, which is nothing but sigma square by n. So if x is normally distributed, then your xi's are normally distributed, and therefore its linear combination is normally distributed, therefore x bar is normally distributed, and with the help of the properties of the expectation and variance, one can see that expectation of x bar is mu and variance of x bar is sigma square by n. Okay, but for not normal distributed, one needs the proper proof, but yeah, I hope the idea is clear. Okay, so the upshot is if x has some population distribution with mean mu and variance sigma square, your x bar is always normally distributed. Now in the next lecture I will take some examples, and if you have any doubt in this, you can ask me in the comment section. Thank you.